What if a company originally making pharmaceuticals is now racing toward high-performance sodium-ion battery cathode materials? That's exactly what Macsen Labs just achieved. Hello, and welcome to the Rigaku vlog on industrial battery advancements. I am Zijun Wang, a materials scientist and R&D consultant with years of experience helping battery companies solve material and quality challenges. In this episode, let's have an overview of Prussian White cathode material for sodium-ion batteries. Prussian White is a framework material with open channels that let sodium ions move in and out. The 2025 Nobel Prize in Chemistry highlighted framework chemistry, the same design principle behind this material. As a cousin of the MOF family, Prussian White uses its lattice to store and transport sodium ions, making it a strong sodium-ion battery cathode candidate. Now, let's dive into it. In July 2025, a few media reported a breakthrough of Macsen Labs on producing Prussian White for sodium-ion batteries. One of the major aspects of this lies in the performance. The material is reported to show a specific capacity of 160 mAh per gram with good cycling life. However, due to the provisional status of the patent, at this moment, we are not able to see how this product differs with that from other manufacturers. But to have an intuitive view of its specific capacity, here's a side-by-side comparison of LFP versus Prussian White. These two materials have similar theoretical capacity, but in reality, both exist a range due to factors such as purity, crystal defect, particle size, morphology, doping, coating, and formulation. Achieving a 160 mAh per gram capacity or above places Prussian White on par with lithium iron phosphate at its top performance. So chemically, what is Prussian White? Let's refer to the work from Dr. Goodenough's group. It is the fully reduced analog of the well-known Prussian blue pigment. Here, oxidation state of the transition metal is the defining difference. Prussian blue has mixed iron 2+ and 3+ centers, so only one redox electron per formula. On the other hand, Prussian White has fully reduced 2+2+ network, unlocks 2 electron capacity. The structures can be solved by X-ray diffraction. It's a cyanide-bridged ion framework. Manganese and iron are coordinated by different atoms of the cyanide group. Iron by carbon and manganese by nitrogen. The quantity of each species can also be estimated using Raman spectrometry. During charging, electrons are extracted from the Prussian White lattice as iron 2+ is oxidized to iron 3+. These extra positive charges are simultaneously balanced by the movement of sodium ions out of the lattice. To provide you with first-hand structural data with different chemical composition, I used micro-ED to analyze nano-sized single crystals of different Prussian White. This phase contains approximately 2 interstitial water molecules per formula unit. Unlike the previous cubic structure, this sodium ion cage are distorted and sits in a monoclinic unit cell. In the structural model, oxygen atoms from water molecules are shown as red spheres, while sodium atoms are depicted in yellow. The crystallographic solution indicates that each sodium ion is coordinated to one water molecule, which is believed to enhance sodium ion mobility, but at the same time compromises long-term structural and electrochemical stability. Overall, the stoichiometry is closely linked to the structure, which in turn is largely determined by the synthesis conditions. Although this company's US provisional applications aren't publicly accessible, we still can peek into previously published papers by other researchers. The process is fairly straightforward. To make the manganese Prussian White, manganese nitrate solution is added dropwise into a solution of sodium chloride and sodium ferrocyanide under stirring. the white precipitate was obtained. To synthesize the ion Prussian White, which is the one reported in the news, first reacts sodium ferrocyanide with ascorbic acid to make Prussian blue. The Prussian blue is further reduced by sodium borohydride to produce Prussian white crystals. This method doesn't involve ferrous chloride or sulfate. All transition metal centers here are in the +2 oxidation state, which underpins its 2-electron redox chemistry in sodium ion cells and enables its high capacity. For your reference, here is an incomplete list of industrial methods described in patents. Please pause and check on them if needed. If we dive deeper, we can see that Prussian white can crystallize into 3 principal framework symmetries, driven by its water content and vacancy level. The as-synthesized, sodium-rich, hydrated Prussian white adopts a tilted monoclinic cell. Interstitial and coordinated water molecules induce octahedral tilts and lower symmetry. This phase is typically straight from aqueous co-precipitation. Partial dehydration removes most interstitial water but leaves the framework slightly distorted, yielding a rhombohedral phase. It balances higher symmetry with residual lattice water and vacancies. Transition from the monoclinic phase to rhombohedral phase is kinetically controlled by temperature and atmosphere. The cubic phase is observed when there is relatively low sodium content or after a dehydrated rhombohedral phase reabsorbs water. The cubic Prussian white is the phase that exhibits isotropic sodium ion channels with a potential to peak rate capability. Let's take a look at how the structures are linked to the performance. The hydrated monoclinic phase has high water content, suffers from low reversible capacity, high polarization, and rapid fade. First charge shows a broad sloping rise up to about 3.1 volts, followed by a sharp increase to roughly 3.8 volts. Then, an irreversible oxidative feature occurs above 3.8 volts due to water decomposition. To unlock this material's true capacity and stability, careful dehydration are required. In the case of rhombohedral phase, the interstitial and coordinated water is largely reduced. It reaches near theoretical capacity as well as sharpens voltage plateau by reducing water-driven polarization. Lastly, cubic phase in some papers shows good capacities and coulombic efficiency. This structure has the potential to maximize isotropic sodium ion channels for fast diffusion. So why does this matter? From a material standpoint, Prussian white brings fast ion mobility and structural stability. Its open framework, 2-electron capacity, and tunable hydration make it an exciting sodium-ion cathode material to work with. From a supply chain perspective, it leverages Earth-abundant sodium and iron. This directly addresses the industry's biggest long-term constraint, supply security and price stability. And from an industry view, it signals a diversification of players and innovation sources beyond the traditional battery giants. And, as always, I'll keep tracking these updates so you don't have to. Thanks for watching. If you're as excited about batteries as we are, hit like, subscribe, and stay tuned for the next episode.